Welcome to my presentation. My name is Ramon. I'm a test systems engineer working with LabVIEW. I come from a mechanical background. So when I was starting with LabVIEW, one of the things I really liked about LabVIEW is like I could run any piece of code in parallel very easily. However, when working with engineers with other backgrounds, I discovered that there's something called concurrency, and most of the code that you see in LabVIEW that's visually parallel, is not actually parallel, it's concurrent. And hopefully I can show you the difference today and see how that you can spot it in LabVIEW. So I would like to include mention to our giants of female. This is Beatrice Schilling, who was an aerospace engineer for the RAF during the Second World War and a motorcycle racer. She developed, during the Second World War, the Hurricane and the Spitfire fighters. They had a disadvantage against the German jets. So when they were performing nose-down maneuver, the engines of the Spitfires and Hurricanes would float with fuel because they were using carburetors. So she developed a fuel restrictor, and it was so popular among the RAF pilots that they called it the Miss Schilling orifice, which I think is pretty cool. So yeah, parallelism against concurrency, basically what is what. So concurrency we refer to concurrency as the execution of multiple tasks at the same time, but they're never being executed simultaneously. So if we compare this to parallelism, in parallelism we have multiple tasks being executed simultaneously amongst different processes. So that means different hardware also handle different tasks. So if we were to translate or kind of show this in LabVIEW, what it would look like. So something very straightforward, just two very simple tasks. I've tried to keep this presentation quite simple. So we've got a multiplication process and a division process. So visually, these two tasks, as I was saying, they look parallel. People would say they execute at the same time because no inputs from any other tasks or the processes depend on each other. However, this is not parallel. This is concurrent because we don't have any proof that these tasks are not sharing hardware resources while they're being executed at runtime. So what it looks like this, well, probably LabVIEW is the CPU is how it's handling this task, is executing this one, then it's doing one iteration of multiplication, one iteration of the division, then go back to multiplication, division. So they're being executed at the same time, just not simultaneously. So now you may think, okay, so how can I achieve parallelism with my process? Well, LabVIEW provides us with something called for-loop iteration parallelism. So if you right-click on your for loop and you enable iteration parallelism, you have the option to specify the number of parallel instances and also the chunks, the partition size of assigned to each of these instances. In here, for very simple purposes, I've just decided to assign 2 parallel instances. So and each of these parallel instances is assigned to each available logic core. If LabVIEW recommends, because this for iteration parallelism is normally used for more complex tasks, not just a simple multiplication or division. So if you leave it unwired, which is what LabVIEW recommends, LabVIEW would optimize the parallel instances and use the maximum number available of logic cores to find peak performance of your process. So in here, on purpose, I've assigned 2 parallel instances, and each of them is going to be assigned to a logic core, and it's just going to run 3 times, as you see in my display. So normally you will leave the parallel terminal unwired, parallel instances terminal, but in this case I've left it, and I wanted to represent what happened if you create 2 parallel instances and your machine happened to have only 1 core, but 1 core with the capability of running 2 logic cores. So I wasn't that familiar with the terminology, and basically when your physical core can run more than 1 thread, in this case 2 threads, becomes a logic core. So on your Windows machine, if you go to Task Manager, right click and then go Performance, it will show you have 4 cores and 8 logic cores. It's also called as hyper-threading. So this is good for the for loop iterations, but what if we want to do, we want to specify exactly which core we want to assign to our task and have more flexibility outside of our for loop. So in this case, we have the timed loop. So this is on a PC target. If you were to run this on an FPGA target, it would be your single cycle time loop, and you have your loop name, your period, your priority, and you can also assign it as CPU. So in this case, the assigning of the CPU starts with an index of 0 and goes up to an index of the maximum amount of logic cores that your machine has. One of the interesting aspects that I found is that if you assign to each of the loops, you assign logic core that is not available on your machine, your code would still run fine and would still compile, but at runtime, LabVIEW will completely crash. It will quit straight away. So here as I say, we can still manually assign. We've got more flexibility outside the for loop, although I just still included there. But we cannot guarantee, if we really want to program to hardware to make sure that our code executes fully parallel, not sharing any hardware resources, to therefore avoid hyper-threading, because here we can assign CPUs, but we cannot make sure that we are avoiding hyper-threading in our CPU, then we have to go to our friend FPGA. So in here of FPGA, we've got 2 different data acquisition loops. We are acquiring 2 analog inputs, performing some scaling for both signals, and we are turning an LED on depending on whether the input is rising or is falling. So the big advantage of the FPGA programming is we are programming, there's no overhead, there's no jitter. We are programming the actual hardware resources of our FPGA. So how does this look like? We've got in our FPGA, we've got our input output cells, and we've got our logic cells. So I'm probably sure most of you know that you have to be very careful when programming your FPGA due to the finite amount of resources. However, the reason why this is the case is because each process, depending on its complexity, is assigned a specific amount of resources. But this is what allows us to achieve true parallelism. So in here, we're going to have our input from each of our tasks. We're going to do some sort of process like scaling in this case, and then we're going to assign a specific amount of logic cells to that process, and that is going to output and if we have some outputs, like some digital outputs in this case, we're going to use some outputs of our FPGA. So in this case, the resources are finite, but luckily we can achieve through parallelism. So what can we wrapping up, concluding? So we've touched up on what is the difference between parallelism and concurrency. Most of the loops that you see in your codes, especially on running on PC targets, they look parallel visually on your block diagram, but they are not. They are concurrent. We cannot guarantee that neither of those loops is not sharing hardware resources on your machine, so they're most likely concurrent. We've shown you some tools of how to parallelize your code and then to achieve true parallelism with an FPGA. And also, but obviously what I've shown you is a very simple task, especially just multiplying and dividing some double precision numbers. So perhaps what we like in the future is introduce what happens when distantiation of objects or the creation of child classes, and if there's some link that we can sort of like avoid sharing hardware resources when we can do object-oriented programming. Just perform some kind of more complex process, and I would like to perform a more computer complex algorithm and benchmark it and see the actual benefits of parallelism and when it's actually beneficial to use it. And also perhaps one of these very complex algorithms in a clonable VI and see how it handles how it's just not only clonable on the software side, but how that clonable VI is handled by the hardware resources. I think that's everything from me. I don't know if there's some, if there are any more questions, I'm happy to, also you've got my LinkedIn and feel free to message me on there or whatever. But yeah, thank you very much for listening and thank you for the opportunity for presenting.